So we've been talking about complex numbers this chapter, and today we're going to graph complex numbers. So our objectives there, we want to graph complex numbers on the complex plane instead of line, which we'll talk about, and find the absolute value of a complex number by determining its distance from zero. So we've learned about absolute value being distance from zero. So same idea, it's going to look a little different, but still the same definition. It's a number's distance from zero. So before we graph, before we graph complex numbers, we're going to go ahead and graph these numbers on a number line. So we're going to graph the point 7. So let's graph 7. We see we have 0 here and 0, and we want to count up to 7, 1, 2, 3, 4, 5, 6, and 7. So that's our point A. That's thick. That's point A. Point B, so actually maybe we can do this. A was blue. B will do in red. So point B is -4. Go backwards 4. 1, 2, 3, 4. That's B. C will do in this bright green. Hopefully we can see it. 3/4. Well, that's partway between 1 and 2. Here's half, and then 3/4 is halfway between there. That's about 3/4, so that's C. D is pi. Oops. Well, so D will do orange. 3.14. Well, we can still graph that. It's still in place on our number line. So here's 1, 2, 3. 3.14, 1, 5, 9 is about here. But it does fall on our number line, even though it's an irrational number. 3 minus 2i. Well, here's where we run into a problem. We don't have imaginary numbers on our number line. We have a 3, but we don't have minus 2i. And really, when we have a number line, up until now, this is really called our real number line. It's called the real number line because it's only real numbers. We drop the word real because it's just easier and quicker to say number line, but this is a real number line, and so therefore we can't have complex numbers. So you see that right here. We cannot graph complex numbers with imaginary parts on a number line. We can, however, graph them on a complex plane, and that's what we're going to learn about today, a complex plane. The complex plane looks and kind of acts very similar to the Cartesian plane. Cartesian, that's just a regular xy. We don't say Cartesian a lot, but that's what we have here at the bottom right-hand corner of our screen is a Cartesian plane with an x and y axis. Now, it is not a Cartesian plane. It is the the complex plane. And we can put complex numbers on there, and I should remind you that these numbers up here that we mentioned before, these still 7 and -4 and 3/4 and pi, they're still complex numbers. They're just even in a smaller subgroup, a smaller set of real numbers. And so they are complex numbers, so they can be graphed on a complex plane also. So graph the following numbers. Well, let's talk about our complex plane first. Our complex plane, instead of having an x-axis and a y-axis, we have our real axis is our normal x-axis, or what we think of as our x-axis, but it's our horizontal axis, and our vertical axis is our imaginary axis. And so that makes it fairly simple to graph because these are going to look so much like graphing on a Cartesian coordinate plane with x and y. So 3 minus 4i, that's definitely a complex number. The real part is 3, the imaginary part is -4. And so all we do is we go to 3 on our real axis. So here's our real axis. We're going to go to 3, and then from there we're going to go to -4i. So we have to go down 4 because the vertical has to do with imaginary. So here is the point 3 minus 4i. So we'll underline that in blue. So that's our blue point. Graphing the point -3, that's not an imaginary number, but it still is a complex number. It's just that it's -3. It does not have an imaginary part. We can graph this one in red, and so we'll come over here. Here's our 0. We can call it our origin still, and we want to go to -3 on the real axis. That's our real part. So -1, back 2, back 3. There is -3. -2 plus 5i. The real part's -2, so we go back 2 and a plus 5i. So that means we go up 5, 1, 2, 3, 4, and 5. A little bit off our graph there. We can estimate there. So that's our -2 plus 5i. And the last part is just the imaginary unit. It is just I. Oh, that's yellow, not real dark. We'll just go black. And so I, well, that means we're not going anywhere on our real axis. This is like a 0 plus I, so we're just going to go up to I. And so here is I on the complex number I on that complex plane. And so graphing is as simple as that. And so there's those 4 points. Now what we're going to do is we're going to get into finding the absolute value of numbers. So graphing complex numbers is fairly simple. Absolute value of complex numbers is also fairly simple. It's still our definition that we've learned and known from before, that we've used before. It's kind of a geometric distance, our definition, because it has to do with distance. And so we want to find the absolute value of these. So what we'll do is we'll graph these. We'll look at them, finding their absolute value, and then we can come up with an idea that will always work for these. And that's really what algebra is about, is generalizing. So here we have 3 minus 4i. We graphed that before. Here's our 3 minus 4i. And we want to find its distance from 0. Well, right here in the center is our 0. Because this is 0 on the real axis and 0 on the imaginary axis. So that's 0. That's called our origin. 0 is also called the origin. And so we want to find the distance. Well, the distance for this one is this distance right here. And now we really are going to go back to geometry. We want to find that distance. And so we want to find the length of this little segment here to find the distance from 0. And so what we can think of here is we have this right triangle. And if we have a right triangle, if we know these two sides, well, our real part was 3. This length was 4. It's actually -4. We can find this part here of our right triangle, our hypotenuse. So what we do here is the absolute value, we're going to find the distance, let's call it, say, d. d squared equals 3 squared plus 4 squared. So remember Pythagorean theorem, c squared equals a squared plus b squared. And this is in a right triangle where c is the hypotenuse and a and b are the legs. That's a quick reminder for you. So d equals, d squared equals 9 plus 16. d squared, we're going to take the square root of both sides, but first we add them. It's 25, and d equal, we're going to take the square root here. And notice I didn't put plus or minus here. There's a reason I didn't put plus or minus, is because we're finding absolute value. Absolute value is a distance, and therefore absolute value is never negative. So we don't need the negative part. So the distance is just 5, so the absolute value is 5. And so we really still do use the absolute value symbol, so we could write the absolute value of 3 minus 4i is equal to 5. 3 minus 4i is the absolute value of that. Whoop. That is not what I wanted to do. that's equal to 5. And we can go through and we can do these other ones too. Some of them are going to be simpler than others, because this next one here, this negative 3, we actually already know the absolute value of negative 3, but if we look at negative 3, we want its distance from 0 or the origin. Well, we can look at this and pretty easily see that the distance is 3. We learned a long time ago that the absolute value of negative 3 is 3. So that's nothing new or profound to us. Over here, negative 2 plus 5i. So we'll do this one in green like we did before. Negative 2 plus 5i. That was actually off our graph a bit. It's up there. And to find that distance, we still can make a right triangle. We saw that this was 2. It seems a little too light, so I'm going to go ahead. This is 2 and this is 5. And so our distance is going to be, and we can put the negative in there, negative 2 squared plus 5 squared. So d squared is 4 plus 25, which is 29. Take the square root of both sides, and you get d is the square root of 29. So the absolute value is equal to the square root of 29. It's not plus or minus, because remember, absolute value is positive because it's a distance. And then this last one here, I, we want to find the absolute value of I. We graphed that before. That is just this spot right here. Here's I. And see, the distance from 0, we see that pretty easily is 1. So we can find the absolute value by graphing it and then finding its distance from 0. We use the Pythagorean theorem to help us do that. I want to go ahead and look at this generally to look at the absolute value of any complex number. So I want to look at the absolute value of a plus bi, because that's a general complex number. We could graph that on our complex plane, where this is our real and this is our imaginary. Let's just say a plus bi ends up here. So we went over a and up b, and that's our point, a plus bi. If we wanted to find that distance, that absolute value, I'm sorry, it would be that length there. Let's call it d, because it's its distance from 0. And we see that d squared, using Pythagorean theorem, is a squared plus b squared. And I can't add those because I don't have anything in there yet. So a squared plus b squared. To solve that, we would take the square root of both sides. And so we see that it's just the square root of a squared plus b squared, which is our absolute value. So this really can make this a lot simpler if we remember this. We don't have to memorize this. I'm not always into memorizing. It is helpful though, because we could always graph it and find it. But absolute value, looking at this general one, is always the square root of a squared plus b squared. Okay, absolute value is always the the absolute value of a plus by is the square root of a squared plus b squared. Let's go back. I'm just going to remind you of this. We had, let's do this one, this negative 2 plus 5i. Let's just test this here. Absolute value of negative 2 plus 5i. I'm not going to graph it this time. I'm just going to realize that it's going to be equal to the square root of a squared, which was negative 2 squared, plus b squared, which was 5 squared. Negative 2 squared is 4, 5 squared is 25, and we get the square root of 29. So obviously we do see that there is a benefit to knowing that the absolute value of a complex number is the square root of a squared plus b squared, and it makes it a lot simpler, then you don't have to graph it. So looking back at our objectives, we wanted to graph complex numbers on the complex plane. We did that. And we wanted to find the absolute value. And we did that. First of all, we did it just by using a right triangle and using Pythagorean theorem, but now we know that the absolute value of any complex number, I'm saying this a lot because it's important and helpful, is the square root of a squared plus b squared, the square root of the real part plus the real part squared plus the imaginary part squared, and the square root of that. So now you can graph complex numbers, pretty simple to do, and you can find the absolute value of them